Hello, in this video we're talking about Faraday's law. This is the beginning of our unit on induction. Electromagnetic induction is what we're talking about. Topic D.4 in the data booklet, an HL topic where we really get to dig into the fun and exciting ways that electricity and magnetism are related. Here is a little animation of a famous simple experiment that you can do. Here's a little FET sim doing it, which is we have learned a little bit already that there's a relationship between electricity and magnetism when there is motion. If a charge is moving, if electric charge is moving, that's how you get a magnetic field. So the question would be, what if the opposite happens? What if the magnet is moving? We see this. If you move a magnet near a conductor, that is all you need to make electricity happen, because electricity will happen. Current will flow in this kind of example. So we call this electromagnetic induction. If there's a conductor, like a wire, a spool of wire or something, subjected to a changing magnetic field, we induce a current. So a current is induced is the word we use a lot for this stuff. That's the idea of induction. It's kind of generated, created in the wire, is more or less what we mean when we say induced. So when there's motion of this magnet, the magnetic field inside of the coil is changing. What you notice in this experiment is if the magnet is just sitting inside of the loop, nothing happens. There's no current at all. It's only when there's a changing situation. It is all about change. It's all about motion. That's the link between these two things, electricity and magnetism. So often the way we'll say this is there's an induced EMF caused by the changing magnetic fields because a current is flowing. We defined EMF as this idea of an electromotive force, which is an annoying word because it's not really a force, it's a voltage. But EMF is something to do with the work per unit charge that a thing is doing as it pushes charge around in a circuit. So the induced EMF refers to the energy, the work being done to move charges about inside of that conductor. So induced EMF, induced current, those are the things we're going to talk about. To quantify how much like EMF, how much voltage, how much current you get, it turns out it depends on a fun little thing called flux. Flux is a way to talk about what's happening with the magnetic field inside of usually like a coil of wire, like a loop. So how big that voltage you get, and you can see this too at the experiment, it depends on how strong the field is. So we can picture that as like the number of field lines going through the coil, and also how quickly the field is changing. So you can get a big voltage by either having a strong magnet or moving the magnet quickly. So flux, magnetic flux, is going to represent the number of field lines passing through a certain area, usually in something like a loop of wire. It represents that it's not literally a number, so we're going to look at how we calculate it. There's a symbol. We use phi, P-H-I, Greek letter phi for this, and the unit we measure in is called the Weber. A Weber is a Tesla times a meter squared. We'll get more into that in a second. So flux has to do with, like, you can think of it, it's not, because the field lines are sort of a generic thing, an arbitrary thing, but you can picture it as the number of field lines. Like the more field lines that are going through the loop, the bigger the flux. Okay, the number of the field lines is the way to think of this. So there's a few examples here. We have at the top one, this is just like two loops of wire, one with a stronger field than the other. This one on the right, field lines are closer together. That would represent a stronger magnetic field. There's a greater flux, magnetic flux through this loop than through this loop because there's more field lines going through the loop. Other ways you can change flux, though, is you can put some angle between the field and that loop. Picture a hula hoop, and a bunch of lines going through it. If you angle the hula hoop, less of those lines are going to go through it. Some of them are like passing overhead, and some of it's like up above and it's going under them. Whereas over here, if it's straight up and down and like, perpendicular to the field or something like that, then you get maximum flux when they're at an angle like this. So the angle can change the amount of flux, the amount of field lines that are going through the loop. And of course, you could change how big your hula hoop is. A bigger hoop will capture more field lines, so there's more flux here. Okay, so the amount of flux is really the thing that this is going to depend on. And remember, this is all about change. So what we're really going to care about is the change in flux, which we'll get to in a second. There's an equation for flux. So here's how we do it. It has to do with the magnetic field strength multiplied by area. And officially, it's the magnetic field strength normal to the surface. This is the equation. This is what you want to think of about what flux is. This is how you figure out a number for flux. Flux is B times A times cosine of theta. Okay, in this case, as usual, B is our magnetic field strength, which we measure in Tesla. A is the area of the surface, or the area inside the loop. This is usually something like a coil of wire. Often they are square or rectangles. So you do like the area of this rectangle or square, or the area of like a circle if it's a circular loop. And theta, this one, be careful. Theta is the angle between B and the normal line to the plane, because your loop or whatever is a plane, a 2D plane. And so what we picture is a normal line. This is kind of a way we define the direction, if you will, of a plane as we draw this normal line. So you got to picture, like, if you're looking at the table in front of you and your loop of wire is on the table, put your pencil straight up and down at the table in front of you. That's your like reference line that you measure the angles from. So if sometimes you want to do these backwards, so just be careful. This is the angle we're going to be talking about. If the field is going straight down into the loop, then the angle is 0. And if the field was coming in, from the side like this, the angle would be 90. Do, as always, a great tip in general when you have equations that have like cosine or sine in them. If you're not sure, or just to check your work, always think about what happens with 0 and 90 and does that make sense. The idea we want to build here is that if these lines are coming straight into the loop, then I have a lot of flux. So that must be 0 degrees. You might be tempted to call this 90 degrees when you do these problems. But if I look at the math, that would mean I have 0 flux when it's coming in like this. And that doesn't make sense. So that can help you remember like which way this angle goes. Okay, I want cosine of this to equal 1 when the B field looks like this. So this is the angle we're talking about. All right, another fun term you're going to see is magnetic flux density. This is a funky way to say field strength. Okay, so a second ago we defined a Weber as a Tesla times a meter squared. That's weird. Much better way to think about most of this stuff, I think, is to think of a Tesla as a Weber per square meter. So Tesla is a Weber per square meter. Weber's is like the kind of amount of field lines. So how many field lines do you have per square meter of area? In other words, how dense is your flux? So just know when you see the term magnetic flux density, it's a fancy or scary way of saying B, the magnetic field strength. Here is a very, very fun little picture you can have in your brain from good old Cognity, where you can think about the difference between flux and flux density. So say you get yourself a box of spaghetti, a nice pound of spaghetti. There's a lot of spaghetti in there, right? Like many, many, many spaghetti. You can picture those as the field lines. Whether that spaghetti is crammed into the little rectangular box and it's all really close together, or whether you drop all that spaghetti into a big giant pot, the total number of spaghetti is the same. So the flux is the same. The amount of like lines going into or out of your opening is the same. The difference is in the box, the spaghetti density is very high. And when you drop it in the pot, the spaghetti density is less. So in both of these cases, the analogy here is the flux is the same. The total amount of lines is the same, but the flux density is different. It's much higher here because you got the same, amount of pasta per square meter. Same amount of pasta, but over a bigger distance. So the pasta per square meter is less here. Yeah, so you have like a weaker field, stronger field. This is just another way to think about what we mean when we say as the field lines, when we draw field lines, if they're far apart, that represents a weak field. If they're close together, that represents a strong field. Okay. Another fun flux term you'll see is called flux linkage. And this comes up a lot because usually we don't have just one loop of wire. When we do stuff like this in real life, we make loops with many, 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 loops of wire all kind of strung together. So to account for that, we have a thing called flux linkage. If, for example, up here, I have a magnetic field going through, if I just picture this one kind of area, this one, let's say it's a square loop of wire, I have a certain amount of flux. If there's two of these and they're connected together somehow, I would have double the flux. And if there's three of them, I would have triple the flux, okay? Because the field lines go through the same area like 3 times. Okay, you can kind of think of it like you're also just like figuring out the total area that it goes through. So I'm going to take the area of this one loop and multiply it by however many loops. This is another good way to think of this. So just know flux linkage, if you see it and it shows up in an equation in a way that we'll look at in a second, you can think of it as big N times the flux, where flux is that equation we just looked at, BA cosine theta. You're going to see both of these terms, loops or turns, which again represents when we do this for real, we usually take a piece of wire and just wrap it and make a circle and just keep going and going and going. So you have a loop with many turns is usually how we say it. So you might have 100, little turns going around to make a big giant loop of wire. And then you get to multiply your flux by 100. Get yourself a nice big voltage. All right, so it'll look something like this. So this would have, 1, 2, 3, 4, 5 turns is how we would say it. And this would give you 5 times the flux that you would get if you just had one loop. Okay, this brings us to Faraday's law itself. And Mr. Faraday did some experiments here and figured out how big is the voltage that you actually get. What does it depend on? And it turns out what it depends on is the rate of change of flux. That's what it is. So here it is. Here's Faraday's law. We use an epsilon squiggly looking E for the induced EMF. Especially for this unit, you can just think of that as voltage. All right, so sort of the voltage you get from this whole crazy changing magnetic field situation. Here's where that N shows up again. So this is, again, for when we have something like a coil of wire with multiple loops. We use N for the number of loops there. And best to think of this, whenever you see something like this, as one big quantity, the rate of change of flux. All right, you're changing flux over your change in time. How much did the flux change and how long did it take is what you're kind of doing. Calculus people, if it helps, picture these as lowercase d's. That's really what it is. It's a derivative. But this is IB physics, so you don't need to know that. All right, the rate of change of flux depends on how the magnetic field angle or area change with time, because remember, those are the things that influence flux. So any one of these things can be changing with time, and you will see different examples of all of those. In either case, though, really remember just what you do up here when you have a delta, a change. You're always going to do final flux minus initial flux over the, time 2 minus time 1, the amount of time elapsed. So if the B or A or angle are changing, you plug them in at the beginning, plug them in at the end, and this is the value you're finding the change in to go into this equation. All right, let's try a problem and see what this kind of looks like. Here's the type of thing you will see. We have ourselves this little square loop of wire. You just take a wire and kind of bend it and turn it into a square so that the math is easy, I guess. And it's perpendicular to a uniform magnetic field this big, 0.36 Tesla, directed out of the plane of the paper. Remember, our 3D vectors, the dot means it's an arrow coming right at your face. So we want to do a couple things, calculate the flux, and then some stuff's going to happen. Okay, so let's go to that. All right, let's try these problems. So I want to first calculate the flux through the loop for part A. Relatively straightforward. So this is just practicing using our new equation for flux. We want to know our best friend, the data booklet, and be like, oh, flux, I know that. That's the this thing, the phi looking thing. And it's b times a times cosine of theta. So I'm going to plug in b and a and theta and see what I get for flux. That's it. B is given. There it is. That's B. So far, so good. All right, I'm going to need A. I'm going to need the area. What they tell me is that the square loop has side lengths of 15 centimeters. I'm going to be making at least a little sloppy sketch in my, paper 2 problem on the IB exams when they give this to me, so I picture what's happening. So it's 15 by 15. I want the area. Be careful with, centimeters, meters. There's 100 centimeters in a meter. There's a whole lot more than 100 square centimeters in a square meter. Your best bet always is to just convert to meters first, so you don't have to worry about remembering to square your 100 scale factor or what have you. So I'm just going to call that 0.15 meters squared. That's the area. Good enough. Okay, what's theta in this example? Take a moment, see if you can picture what theta is based on how he said it. Theta is going to be 0 degrees. To picture this, remember we're doing like relative to the normal line. So I want to picture, if I look at it kind of side on, there's my little loop and there's like the field coming up through it. So there's like my B field. And we're doing this relative to a normal line. It's not a very normal line. Relative to a normal line. So I picture a line coming straight up from the plane. And that's my reference for theta. So you got to kind of get used to these. For a lot of people, I think you look at the, red arrows here and you think, oh, well, that's like 90-degree angle between that and the loop. But it's not. That's 0 degrees because this black line is what we do to measure that angle. So the arrows in the black line are in the same direction. That angle 0 makes sense to me because it seems like we got a lot of flux. We got a lot of spaghetti going through that loop. So I got to put in 0. If I put in 90, I would get an answer of 0 flux, which doesn't make any sense. I'm thinking about spaghetti. All right, so theta equals 0. I'm going to be a little sloppy here, which means the cosine of theta is just 1. So the flux is just B times A. Nice and easy once I know what I'm doing. All right, so let's just do it. The B, the magnetic field strength, is 0.36 Tesla. And I'm going to multiply that by my area, which was 0.15 meters squared. I'm just going to do all that at once in my calculator. And I should get 0.0081. Flux is my units are Webers, is what a Tesla times a square meter is. I could, I could write this as 8.1 times 10 to the minus 3 would be a better way to show that. Or if I'm feeling fancy, I might call it a milliweber. What about that? Okay, that's flux. So 8.1 times 10 to the minus 3 Weber is the flux through the loop. All right, let's try B. The direction of the magnetic flux is reversed in a time of 0.5 seconds. Calculate the average EMF induced in the loop during the time. Okay, the flux is reversed, which means what we want to picture is the field, I'm thinking, is going to be reversed. Could happen a couple ways. You could honestly flip this loop upside down, would do the same thing. But I go from a flux that looks like this, is how I'm picturing it, to a flux that looks like this, where they're all going in the opposite direction. So the field changes, is how I'm thinking of it, from this way to like less to nothing, and then the field gets bigger and bigger downwards. All right, so there's a change in flux, which means there will be an EMF induced. So we got a flux situation. I'm given a time here. I want to find induced EMF. This is definitely Faraday's law. So for part B, let's do Faraday's law. EMF is equal to negative N, change in flux over change in time. In just a second, I'm going to ignore that negative, and in a lesson or two, we'll learn about kind of why. It's very strange, but this equation really gives you like the size of the EMF. And when you got to figure out the direction, it's a whole crazy thing called Lenz's law. So I'm going to drop the negative in a second. We just care about how big the EMF is right now. Okay, and my number of turns, my number of loops is just one. It's just a single loop. They would have to tell me if it was like multiple stacked on top of each other. So n is just one. I just got to find the change in flux. Well, my initial flux was 8.1, like milliwebers, and we're flipping it to reverse the direction, which means it's going to go from 8.1 to negative 8.1. That's the change that's happening. You can picture it's like this angle is changing from 0 to 180. So I go from BA to negative BA. So my change in flux here is going to be, change in flux is going to be 8.1 minus negative 8.1, I think is 16.2 times 10 to the minus 3 Webers. That's the change in flux. And that takes a time of half a second. So again, once we know what we're doing, the math is usually easy, even though this stuff is super hard. The setup is. Okay, so n is just 1. Again, I'm going to drop the negative sign. I just want to find the size of the volts. And nope, it's 16.2 times 10 to the minus 3 Weber over half a second. Gives me, 32.4 times 10 to the minus 3. Webers per second must be volts. It's an EMF. All right, I'm basically there. I should do my sig figs. I got 2 sig figs, 2 sig figs, 2 sig figs. We should round this final answer to 2 sig figs. So our EMF here will be 32 millivolts is how I like to say that. 32 times 10 to the minus 3, also great. 0.0032, fine, but kind of sloppy. Let's do good notation. Okay, so that's what we got. All right, and let's try the last one. Let's try part C here. Now we get a resistance of the loop, and I want to find energy transferred. Oh boy, I thought circuits were over. This is great news. I get to do more stuff with like resistance and ohms because we're talking about volts. There's going to be current flowing. We're going to use all that stuff. So my new piece of information here is the resistance is 1 times 10 to the minus 3 ohms. Little teeny tiny resistance because it's just a little piece of wire. I want to find the energy transferred. All right, my problem solving skills start and I'm like, geez, okay, energy transferred. Well, I got a resistance. I just figured out some volt stuff. Energy. Well, the number one thing I think about energy is the one thing that I'm never, ever going to forget about in physics, which is power. Power, energy, time. They all go together. Maybe if I find power, I know about the time, I can find the energy. And of course, I have lots of amazing equations in the data booklet that have to do with power when electricity stuff is happening. So maybe I should pick one of these. I think I should pick this one because I have a voltage here and they gave me a resistance. I can find the power, and then now I'm real confident if I know the power, I can find the energy. So let's do that. All right, you can use EMF as voltage in all of these kind of EM induction problems. This isn't like you have a battery with an internal resistance where you have to worry about that stuff. So EMF, you can be pretty sloppy here in this section and just use it as V. So that's what we're going to do. First, I'm going to find the power. I'm going to do that EMF we found. I'll use the rounded value because that's usually how it goes in IB problems. But you're welcome to use the unrounded. You'll get something a little different. So I'm going to take that 32 times 10 to the minus 3 volts, square it, divide it by half a second. Calculator tells me that that will give me an answer of 1.024 watts. I know deep in my heart and soul, I recite it every night before I go to bed. A watt is a joule per second. Power is energy over time. That means to get to energy, super easy. Power times time. Let's multiply our 1.024 joules per second by the time we have half a second, and we get 0.512 joules. There we go. And same thing, last thing, let's round this to 2 sig figs, 0.51 joules. All right, so there you go. Multiple different ways you can use this stuff, your flux equation, your Faraday's law equation, and one example of how you'll put this stuff together with like figuring out the energy, power circuit stuff. Okay, last piece of information you need here is one of the biggest ways we use Faraday's law is in generating electricity. Almost all of the electricity we make and use comes from this. What you do to make electricity, we still do it this way today, is you take a loop of wire and you spin it inside of a magnetic field. This is a generator. It's a thing that's converting mechanical energy into electrical energy. So really like rotational kinetic energy usually is being turned into electrical energy. Because, see if you can picture why, there is a changing flux happening in this situation. So as the flux changes, you will get an EMF, you'll get a voltage, you'll get electricity flowing. And again, all of our like power plants are doing this. And it's some crazy thing, like you take some coal and you burn it and you make steam, and that steam spins a big turbine connected to some wires like this, and it spins a coil around near a magnet and you get electricity. Or you put one of these inside like a wind turbine, and the wind just spins this thing around and it spins a coil and makes electricity. Or you build yourself a nuclear power plant and you split the atom, an amazing feat of technology, and then you use the heat from that reaction to boil water and make steam and spin a turbine and spin a thing around inside of a magnetic field, and you get electricity. Okay, there's some simulations you can play with that show you this happening, but this is the idea. So again, see if you can picture how and why the flux is changing. You go from lots of flux to like no flux, lots of flux, no flux, lots of flux, no flux, and the flux is even changing direction. So as the flux changes direction, you do get a sine wavy kind of EMF. All right, so here's one of those kind of sims showing this. So because the field lines are going through the loop one way in the one orientation and the other way the other time, sometimes the voltage is one way, sometimes it's the other. This is called alternating current. The current that we generate, the current coming out of the outlets in your home is alternating current. This is the main type of current we usually use when we're generating and transmitting electricity, because it's a lot more efficient than direct current, which is the current we usually learn about in IB physics. When you have a battery hooked up to a resistor and current's just flowing through it in a loop, that's direct current. All right, so there's a whole fun world of alternating current and the sine math of alternating current. The IB doesn't really get into that these days. So you just want to know that when you have this situation, a generator, where you're spinning a coil of wire in a magnetic field, you get a sinusoidal EMF. Okay, the other piece of information they want you to know, for some reason, they love this. I don't know why. You don't even learn the sine stuff anymore. But they still want you to know it, so let's know it. The EMF you get in the rotating coil is proportional to the frequency of rotation. Memorize that. Memorize that. It usually comes up. They'll say, the question they love is they say, you got a generator going, now you double the frequency, you double the speed you're spinning it at. What happens to your EMF? And the answer is it doubles. Okay, they're proportional. If you'd like to know why, here you go. This is for calculus people. If you are a student of calculus, if you love calculus, check this out. If not, you can ignore it and just memorize that rule. But if this helps you see where it comes from, Faraday's law is really a derivative. Okay, it's a secret. Don't tell anybody. Don't tell the IB. But it is. It's a derivative. Okay, it's the rate of change of flux. So what we would really do is we would take like the time derivative of my flux equation. Okay, well, I have to get this in terms of t. And we're going to go to some rotational stuff and say the angle, in this case, the angle between the field and the like normal to the loop is changing with time. The angle between the lines and the loop is changing. And I would take the rate of rotation, my angular frequency, use omega for, and multiply that by time to get the angle at any given time. So this would be our little thing to make it a thing we can do this on. So go ahead, try it out. If you love calculus, what do you get when you do this? All right, the fun thing that happens is there's a chain rule. When you take a derivative, this thing comes out front. So you end up with the angular frequency times blah, blah, blah sine. Okay, so you get a sine kind of EMF where it's proportional to omega, okay, the rotational frequency. So this shows you EMF being proportional to omega if you want to know where that comes from, and if this helps you remember when you get to that problem and you forget this from the list of 500 things you memorized for the IB physics exams, this is a good way to get there. Okay, that's lots of stuff about flux EMF, how we make electricity. Lots more to come, so have fun.